Deep beneath one of the most densely populated volcanic regions on Earth, scientists just found something they were not expecting. Not a single discovery, but 3 arriving in quick succession, each one reshaping how researchers understand the ground underneath nearly 1 million people living just west of Naples. Put together, the picture that emerges is exactly as unsettling as it sounds. Campi Flegrei, which translates to the Phlegrean Fields, is not a single mountain like its famous neighbor Mount Vesuvius. It is a caldera, a vast, mostly submerged volcanic depression stretching across land and sea just west of Naples, home to roughly 900,000 people living directly on top of it. Unlike a typical volcano with one visible peak, Campi Flegrei's danger sits hidden beneath the surface, spread across an entire urban landscape rather than concentrated in one obvious location. That structure is part of why understanding exactly what is happening underground has become such an urgent scientific priority in recent years. The first major discovery came from an unexpected source, artificial intelligence. Researchers applied a machine learning model to years of seismic monitoring data collected across the caldera, and the results were staggering. The AI system identified more than 4 times as many earthquakes as traditional detection methods had previously found, uncovering roughly 54,000 seismic events that had gone completely undetected using conventional analysis. Beyond simply finding more earthquakes, the model revealed something scientists had never clearly mapped before: a well-defined ring fault tracing the boundary of the caldera's uplift zone and extending offshore beneath the sea. One of the lead researchers described their reaction from Italian colleagues studying the region for years plainly, saying they were genuinely surprised to see the ring fault appear so clearly once the AI model brought it into focus. That ring fault matters enormously because it gives scientists, for the first time, a precise outline of exactly where stress is, concentrating around the caldera, zones that had previously remained essentially invisible to researchers working with older detection methods. Seismologists have traditionally relied on a painstaking manual process called phase picking, where analysts mark the first faint wiggle of an earthquake signal by eye on a seismogram. Training a machine learning model on millions of labeled examples allowed it to recognize tiny, overlapping seismic signals that human analysts in older automated systems had simply been missing at scale, sharpening the picture of the caldera's internal structure. The same way adjusting a blurry camera lens brings an image suddenly into focus. Campi Flegrei has a well-documented history of exactly this kind of unnerving ground movement, and looking back at previous episodes helps put the current unrest into perspective. During a dramatic uplift crisis in the 1980s, the ground beneath the nearby town of Pozzuoli rose so rapidly and so significantly that the town's harbor became too shallow for boats to dock, a visible, undeniable sign of how much the earth beneath the region can shift in a relatively short window of time. That episode, along with previous unrest cycles stretching back decades, is part of why researchers describe Campi Flegrei's behavior as a recurring pattern of inflation and earthquake activity rather than a single unprecedented event happening for the first time right now. Understanding that historical rhythm is exactly why these 3 new scientific discoveries matter so much, since they finally offer researchers a much clearer picture of the actual mechanism driving a pattern that has been recurring, in various forms, for generations. The second major discovery came from a completely different angle, and it challenged a long-standing assumption about what is actually driving the unrest at Campi Flegrei in the first place. For years, the working theory assumed that rising magma, or gases released from magma deep underground, were the primary force behind the ground deformation and earthquake swarms shaking the region. New research led by scientists at Stanford found something different. The type of elevation changes and earthquake swarms appear to be driven primarily by rising pressure inside a geothermal reservoir, a layer of water and steam trapped beneath a natural rock seal called a caprock, rather than by magma movement itself. Through subsurface imaging and laboratory experiments, researchers demonstrated how pressure building from water and vapor trapped beneath that caprock can trigger earthquakes once the seal finally gives way under the strain. That finding carries a genuinely surprising silver lining alongside its unsettling implications. If the unrest is primarily driven by fluid pressure building in a geothermal reservoir, rather than magma actively pushing toward the surface, researchers suggest the cyclical unrest might actually be managed, potentially by channeling water runoff away from the area, or lowering local groundwater levels to reduce the pressure feeding into that reservoir. That would represent a genuinely unusual scenario in volcanology, an active caldera's unrest, potentially being influenced through deliberate water management, rather than simply monitored and endured until nature runs its course on its own timeline. The Solfatara crater, one of the most visible and heavily visited parts of the Campi Flegrei complex, offers a striking, publicly accessible window into exactly the kind of hydrothermal activity researchers are now studying in far greater depth. Visitors to the site have long been able to see and smell the sulfurous steam vents bubbling up from the ground, a visible surface expression of the same underlying hydrothermal system that the new geothermal reservoir research suggests may be the true engine behind the region's earthquakes and ground deformation. That visible activity, long treated largely as a geological curiosity and tourist attraction, is now understood to sit directly above the same pressurized system researchers believe could potentially be managed through careful water intervention. The third discovery pushed the picture even deeper, quite literally, into the earth beneath the caldera. An international team of researchers analyzed more than 5,000 distant earthquake signals recorded between 2016 and 2022 to reconstruct the deep structure sitting up beneath Campi Flegrei in unprecedented detail. That analysis produced the first clear image of the caldera's deep magma feeder zone, tracing its structure down to a depth of roughly 50 kilometers and identifying what researchers interpret as a region of partial melting within the crust and upper mantle. In plain terms, scientists now have a far clearer picture of the deep plumbing system ultimately connected to everything happening much closer to the surface, information that had simply not existed in this kind of resolution before. All three discoveries emerged from genuinely significant international scientific collaboration, underscoring just how seriously the research community treats the risk sitting beneath this particular stretch of Italian coastline. The deep magma feeder zone research involved cooperation between the Canary Islands Volcano Institute, Italy's National Institute of Geophysics and Volcanology, Madrid's Complutense University, and the University of Geneva. The AI-driven earthquake detection work received support from multiple research initiatives, including a dedicated national project focused specifically on understanding Campi Flegrei's behavior, alongside funding from the European Union's post-pandemic recovery program. That level of sustained, well-funded, cross-border scientific attention reflects just how significant researchers consider the stakes to be for the hundreds of thousands of people living directly above the system. Layered on top of these three major research findings, the surface-level warning signs at Campi Flegrei have continued intensifying in their own right. The ground beneath the region has risen by approximately 1.4 meters since 2005, a slow but relentless uplift driven by the same underlying pressure changes researchers are now working to fully understand. Earthquake activity has been steadily escalating since 2018, and in June of 2025, the region recorded its strongest earthquake since modern monitoring began, a magnitude 4.6 event, part of a broader pattern that included 5 separate earthquakes above magnitude 4 across that year alone. As of the most recent monitoring reports in mid-July of this year, the caldera continues rising at a rate of roughly 10 millimeters per month, alongside geochemical measurements confirming a long-term trend of the underlying hydrothermal system continuing to heat up, with increased fluid emissions being recorded at monitoring stations across the area. One specific measurement from earlier this month adds an especially stark, tangible detail to everything else scientists have uncovered, the kind of number that makes the underlying science suddenly feel immediate and real rather than abstract. Inside a sealed railway tunnel on the edge of the caldera, researchers measured carbon dioxide concentrations reaching roughly 70,000 parts per million, an extraordinarily elevated level that offers direct physical evidence of just how actively gases are currently escaping from the hydrothermal system deep below. For comparison, normal outdoor air typically contains around 420 parts per million of carbon dioxide. A reading in the tens of thousands, even confined within a sealed space, represents a dramatic, measurable signal of the intense degassing happening beneath the surface right now. Officials responsible for monitoring the region have been careful to frame all of this within an important, specific context that separates some genuine concern from outright alarm, since sensational framing alone would do a disservice to the careful, measured scientific work behind these discoveries. Despite everything researchers have uncovered, current assessments consistently indicate no evidence of magma actively migrating toward the surface. The primary short-term risk identified by the AI-enhanced monitoring system is moderate, shallow earthquakes tied to caldera inflation rather than an imminent eruption. That distinction matters enormously for how residents and authorities should interpret all of this new information. The picture emerging from these discoveries is one of a genuinely active, closely monitored, and scientifically fascinating volcanic system under real internal pressure, not necessarily one on the verge of catastrophic eruption in the immediate term. Even so, the stakes attached to getting this analysis right could not be higher. Campi Flegrei sits directly beneath a metropolitan area home to hundreds of thousands of people, immediately adjacent to Naples itself, one of Italy's largest cities. Authorities have spent years actively debating disaster response planning and evacuation protocols for the region, a genuinely difficult challenge, given the caldera's sheer size and the dense population living directly on top of it. Unlike a conventional volcano where evacuation zones can be drawn around a single peak, Campi Flegrei's risk is distributed across an entire urban landscape, complicating exactly the kind of emergency planning these new scientific discoveries are ultimately meant to inform. The broader significance of this research extends well beyond Campi Flegrei itself, offering lessons that could reshape volcanic monitoring far outside Italy. Scientists involved in developing the AI earthquake detection system specifically noted that the same approach could be adapted to improve earthquake risk understanding in other regions equipped with seismic monitoring networks well beyond this one Italian caldera. In that sense, what researchers are learning at Campi Flegrei right now is likely to shape how volcanic and seismic risk gets monitored and understood at other vulnerable sites around the world in the years ahead, extending the value of this research considerably beyond the immediate area surrounding Naples. For residents living across the Campi Flegrei area today, the practical takeaway from these combined discoveries is one of continued informed vigilance rather than sudden alarm. The region remains under intensive, near continuous monitoring by Italy's National Institute of Geophysics and Volcanology, tracking seismic activity, ground deformation, and gas emissions in extraordinary detail, informed now by considerably more precise scientific tools than existed even a few years ago. Any significant changes in these carefully monitored parameters would be communicated promptly to the public, according to the agencies responsible for tracking the caldera's behavior around the clock. Before you go, if you want to stay updated on how this research and the underlying unrest at Campi Flegrei continues developing, make sure you like this video and subscribe, because we will be tracking exactly what scientists uncover next. Beneath one of the most densely populated volcanic regions on the planet, scientists have just gained a dramatically clearer picture of what is actually happening underground. A hidden ring fault, a pressurized reservoir driving the unrest, and a deep magma system now mapped in detail for the very first time. Genuinely terrifying and genuinely fascinating may turn out to be exactly the same thing at Campi Flegrei. Keep an eye on how Italian monitoring agencies describe conditions at the caldera in the months ahead, not just whether another earthquake makes international headlines. Updates referencing reservoir pressure management, revised risk assessments, or newly detected fault structures are the clearest sign that this rapidly evolving scientific picture continues shaping how officials plan for the hundreds of thousands of people who call this extraordinary and genuinely unpredictable patch of Italian coastline home.